Welcome to the lecture series on CFD, Part 1. This is lecture 17 on fractional step methods for the solution of Navier-Stokes equations. This lecture is about fractional step methods for the solution of Navier-Stokes equations. First, the basic ideas behind this class of methods will be explained, followed by the description of non-iterative schemes. The issues related to the treatment of convection and viscous terms are highlighted because they affect both the stability of the method, that is, the limit on the usable time-step size, and the accuracy of solutions. Special attention is paid to the iterative implicit fractional step methods, which were first presented in the 4th edition of the book, and which are applicable to both steady state and unsteady flows. Application of the method to solving the Navier-Stokes equations using Cartesian grids and a fully staggered arrangement of variables is described in detail. Each step in discretization of all terms in the momentum equation is described, as well as the derivation of the pressure correction equation. The corresponding computer code, in which all these steps can be identified, will be provided as a supplement to Lecture 19. The basic principles of fractional step methods can be summarized as follows. Compute an estimate of the velocity field at the next time step using information, that is, velocity and pressure fields, from the current time step. Then solve a Poisson equation for pressure or pressure correction equation derived by imposing continuity constraint upon the new velocity field using a simplified momentum equation to derive a relation between velocity corrections and pressure correction. Then use the computed pressure or pressure correction to update the predicted velocity field so that it is divergence free. Because of an approximation applied in the second step, the corrected velocity field does not satisfy the correct form of the momentum equation. This step can be corrected by introducing outer iterations within time step. There are many versions of fractional step methods, depending on approximations used and discretization details. Here, only a few versions will be described in detail. The fractional step method will be explained using the coordinate-free vector and operator notation for the Navier-Stokes equations. Source terms are ignored because they do not affect the solution methodology. The continuity equation and the vector momentum equation for an incompressible flow are given by these expressions, where S is the viscous part of the stress tensor as described in slide 14 of lecture 16. I am using this example to demonstrate something that I have never thought of before starting collaboration with Joel and Bob, whose teams have used fractional step methods extensively at Stanford University. One does not have to use the same time-advancing method for each term in momentum equations. We require that the continuity constraint, that is, a divergence-free velocity field, is satisfied at each time step. For the momentum equations, we use Crank-Nicolson scheme to advance viscous terms and midpoint rule for pressure and convection terms. That is, these terms are evaluated at the midpoint between time levels Tn and Tn plus 1. While pressure is stored at the time Tn plus 1/2, that is, staggered in time by a half time step, the velocity is computed at the midpoint explicitly using Adams-Bashforth method. Discrete operators C, G, and L are used to denote discretized convection, pressure, and viscous terms, respectively. Which approximations are used when discretizing these terms is not important, which is why we are not dealing with these details here. Examples will be given in slides 15 to 21. Thus, the set of equations which we aim to satisfy at the new time level Tn plus 1 is given here. If central difference approximations are used in space, the scheme is second-order accurate in both space and time at Tn plus 1/2, where the new pressure is to be determined. The Adams-Bashforth representation of convection term at Tn plus 1/2 is given by this expression. It represents a linear extrapolation from solutions at times Tn minus 1 and Tn, half time step forward to Tn plus 1/2. Because momentum equations contain both velocities and pressure as unknowns, we cannot in one step advance both variables. Therefore, we first compute an estimate of the velocity field at time tn plus 1, which is here denoted as v star, by using pressure from previous time step. The momentum equation solved is thus given by this expression. Obviously, we need to correct the velocity v star by updating the pressure one time step forward. We use momentum equations to compute the velocity components, so the continuity equation must provide a means for updating the pressure. We choose to compute the pressure correction, which is defined as the difference between pressure values at the new and the old time step. A relation between velocity correction Vn plus 1 minus V star and pressure correction P prime can be obtained by subtracting the momentum equation solved, given by this expression, from the momentum equation that we want to be satisfied at the end of the time step, given in preceding slide. However, that relation is too complicated because of the necessary correction in viscous terms, so we introduce an approximation and require that the corrected velocity satisfies this form of the momentum equation, in which the viscous terms at the new time level remain expressed through V star rather than Vn plus 1. The error introduced by this approximation will be analyzed in slide 8. By subtracting the first equation from the second equation, we obtain this relation between the corrected velocity Vn plus 1, predicted velocity V star, and the pressure correction P prime. Now the continuity equation comes into play. We require that the corrected velocity is divergence-free, thus we apply the divergence operator to both sides of this expression. Note that I keep the density in the equations, although it is constant in incompressible flows, to retain the same dimension and physical meaning of each term. It also helps later when we derive the solution method for compressible flows. The divergence of the left-hand side must be 0. The time step can be taken out of divergence operator, and we thus arrive at a Poisson equation for pressure correction. The mass imbalance resulting from the predicted velocity field obtained by solving the momentum equation with pressure from previous time step acts as the source term in this equation. The above pressure correction equation is similar to pressure equation from slide 15 of lecture 16. The advantage of the pressure correction equation is that we can define boundary conditions for it. Where the velocity is specified, its correction is equal to 0, and this relation dictates that the gradient of pressure correction be equal to 0 there. If pressure is specified at a boundary, then the correction must be 0, but the velocity correction is non-zero. It is proportional to the resulting gradient of pressure correction at boundary. In Cartesian coordinates and tensor notation, the above pressure correction equation looks like this. When this equation is solved for P prime, both pressure and velocity can be corrected. The velocity field satisfies then simultaneously the continuity equation and the simplified momentum equation. The implications of the approximation introduced in the momentum equation as outlined in the preceding slide are analyzed in the next slide. We rewrite the relation between velocity correction and pressure correction to relate V star to pressure correction P prime. If we now replace V star in the simplified momentum equation, which is satisfied by corrected velocities and pressure fields, by the right-hand side of this expression, we obtain the following equation. We have solved this equation, but we wanted to solve the blue frame part. The red frame term is therefore an additional discretization error resulting from the introduced approximation. Note that pressure correction can be expressed as the product of time derivative of pressure and time step, as given by this expression. Therefore, the error term is proportional to delta t squared, and is thus consistent with second-order discretization error of the overall scheme. However, this is still an extra error whose magnitude may be high relative to other errors. The order states only that it reduces proportionally to time step squared. Any explicit time advancing scheme can be used for convection terms. The pressure correction equation remains unchanged. One can also apply Crank-Nicolson scheme to pressure term so that new pressure is defined at the time level Tn plus 1 rather than Tn plus 1/2. In that case, only 1/2 of pressure term is updated. A factor 2 appears on the right hand side of the pressure correction equation. One can also advance viscous terms using an explicit scheme, but this can impose a much lower limiting time step for stability reasons if small cells are present or viscosity is high than is required for accuracy reasons. The convection term is non-linear. A linearization is required if an implicit or semi-implicit time advancing is used. In a semi-implicit method, the mass flux making velocity is advanced using an explicit scheme, while the transported velocity component is from the new time level Tn plus 1. In an implicit iterative method, even more choices are possible. One can first iterate on the nonlinearity of convection terms and possible deferred corrections if high-order discretization in space is used, and then solve the pressure correction equation accurately to ensure that the corrected velocity field satisfies the continuity requirement. Another option is to include the pressure correction equation in the outer iteration loop within a time step. It then does not have to be solved very accurately in each outer iteration, and the splitting error described in slide 8 is eliminated through iterations. Fully implicit methods can also be used to compute steady-state flows. Time marching is still needed in any fractional step method, but time accuracy is not important when we march toward a steady state. Only the final solution is of interest. One such method is presented in slides 12 to 14. Non-iterative fractional step methods are believed to be more efficient than iterative methods when computing unsteady flows because the outer iteration loop is missing. However, all non-iterative methods are partially explicit and subject to limits on time step size for stability reasons. The stability imposed time step limit may be too restrictive. Often larger time steps would provide sufficient temporal accuracy. The computing overhead of iterative fractional step methods is not as large as many people think for the following reasons. The overhead for solving momentum equations multiple times is not very high. Inner iterations converge much faster in momentum equations than in the Poisson equation for pressure correction. The splitting error is eliminated throughout the iterations, thus for the same time step, the accuracy is higher than in non-iterative schemes. The overhead for solving the pressure correction equation multiple times in the iterative scheme is also not very large because it is not solved to a tight tolerance in each outer iteration as when a non-iterative method is used. Computing times with different schemes and time steps will be compared in lectures 19 and 20. A fully implicit fractional step method with the acronym IFSM will be explained using the quadratic backward scheme for time marching. See lecture 13. Convection, viscous, and pressure terms are all evaluated at the new time level Tn plus 1. Prediction and correction of the solution at the new time level Tn plus 1 is repeated within an outer iteration loop with the aim to update all nonlinear terms, deferred corrections, and simplifications introduced when deriving the pressure correction equation. At outer iteration m, the following form of the momentum equation is solved. Here, V star is the predictor value for the mth outer iteration. It will be corrected to enforce the continuity requirement so that Vm is divergence free. Pressure is taken from the previous outer iteration. An equation system needs to be solved to obtain V star. The nonlinear convection term is linearized, usually using Picard iteration scheme, that is as Vm minus 1 times V star. We now require that the corrected velocity Vm and pressure Pm satisfy this form of the momentum equation. By subtracting the momentum equation solved in the predictor step from this one, a relation between velocity correction V prime equal Vm minus V star and pressure correction P prime equal Pm minus Pm minus 1 is obtained, given by these expressions. Note that velocity is updated only in the unsteady term, not in convection and viscous terms. This approximation is updated through auto iterations. The next step is to impose the continuity requirement onto Vm to obtain the following Poisson equation for pressure correction P prime. The figure on the right shows the flow chart of the implicit fractional step method. After solving the momentum equations for V star, we solve the Poisson equation for P prime and correct velocities and pressure to obtain Vm and Pm. Unless convergence criterion is already satisfied, we increase the auto iteration counter and repeat the steps above. Once the convergence criterion for auto iterations is satisfied, that is, both velocity and pressure corrections are negligible, we set Vn plus 1 equal Vm and Pn plus 1 equal Pm and proceed to the next time level. Linear equation systems for V star and P prime do not have to be solved to a tight tolerance as in the non-iterative schemes. Reduction of residual levels by circa 1 order of magnitude usually suffices. When computing steady-state flows, implicit Euler scheme is used instead of quadratic backward, and only one auto iteration per time step is performed. Let us now go step by step through the complete discretization and solution process using finite volume method with staggered grids and the implicit fractional step method described in slides 12 to 14. The mass conservation equation and the momentum equation for the velocity component ui in integral form are given here. We need to approximate surface and volume integrals using variable values from control volume centers to obtain one algebraic equation per control volume. This is the control volume on which mass conservation is imposed. It is also used for all scalar variables like temperature, concentration, or turbulence model variables. Pressure is stored at centroids of these control volumes. P denotes the cell center, lowercase letters denote locations at cell surface, cell face centers, and cell corners, while uppercase letters E, W, N, and S denote centers of immediate neighbor cells sharing faces with the cells centered around node P. Control volumes for velocity components are staggered, moved by half cell width to the right for U velocity and half cell upward for V velocity. The same notation is used for all control volumes, but we have to bear in mind that spatial locations differ. P for U velocity is E for the scalar control volume, and P for V velocity is N on the scalar control volume. We shall use discretization methods which are most widely spread both in commercial and in public CFD codes. Time integration using second-order quadratic backward scheme, midpoint rule for surface and volume integrals, linear interpolation, and central differences for derivatives. We start with the rate of change term. The volume integral is approximated by midpoint rule, that is, density and velocity components from cell center are multiplied by cell volume delta V. The time derivative at Tn plus 1 is approximated by differentiating a parabola fit to variable values at 3 time steps, Tn minus 1, Tn, and Tn plus 1. See slides 21 and 22 in lecture 13. The multiplier of the new velocity contributes to the central coefficient in the matrix, while terms involving known velocities from previous time steps contribute to the forcing term on the right-hand side of the algebraic equation. Because auto iterations are performed within time step, the new values will be denoted by the iteration counter m. The convection fluxes must be linearized. Picard iteration scheme will be used. The new flux is then expressed as the product of the mass flux, which is assumed known, and the convected velocity at phase center. The mass flux is computed using midpoint rule for the surface integral over a phase, here the east phase, and velocity from previous auto iteration. The mass fluxes are computed for the phases of the scalar control volume at the end of one auto iteration after the pressure correction equation is solved and velocities are corrected so that they satisfy the continuity equation. At the faces of velocity control volumes, interpolation is required. At the east face of the control volume for u velocity, one can approximate the mass flux by averaging the mass fluxes from these two scalar control volumes. The north face covers halves of two scalar control volume faces, so the mass flux is again half of the sum of the two fluxes. In this way, we ensure that continuity equation is also satisfied for the staggered control volumes. The sum of mass fluxes over all cell faces gives the sum of continuity equation for two neighboring scalar control volumes. The convection flux of ui momentum through the face E is expressed as the product of the latest estimate of the mass flux and the ui velocity at the cell face center. For second order accuracy, the latter will be computed by linear interpolation between two cell center values at nodes P and E. For better convergence properties, first order upwind scheme is used implicitly, that is, to compute the contributions to the coefficients in the matrix, while the difference between explicitly computed fluxes using linear interpolation, here labeled CDS, and upwind approximation will be moved to the right-hand side of the algebraic equation. If the term in brackets is multiplied by a blending factor between 0 and unity, we can also blend the two schemes. This may be useful when the grid is too coarse for the pure second-order discretization, either globally or locally. To compute viscous forces at cell faces, that is, diffusion fluxes, we need to approximate viscous stresses at cell faces. At the E phase, we need tau xx for u velocity and tau yx for v velocity. Central differences are almost exclusively used for this purpose. The derivative of u in x direction is approximated as the difference between velocities at nodes E and P divided by distance. The same kind of approximation is used to compute the shear stress at the east side of the control volume for v velocity. With a fully staggered arrangement of variables, no interpolation is needed. The variables involved are all nodal values from their respective cell centers, v velocities at E and P, and u velocities at corners NE and SE. The pressure terms are computed in a conservative way as surface forces. For u velocity, only pressure forces at E and W faces are relevant on a Cartesian grid, because forces on the north and south face do not have a component in x direction. For v velocity, pressure is needed only at north and south faces. Here is where the staggered arrangement has its main advantage. Storage locations for pressure are exactly where we need pressure to compute the forces in momentum equations. No interpolation is required and no unphysical oscillations can develop. However, this advantage is valid only for Cartesian grids and second-order approximations by midpoint rule. Source terms, if present, are integrated over volume. That is, the value of the volumetric source at the cell center is multiplied by the cell volume. For example, if density is not strictly constant and we use the Boussinesq approximation, in all terms other than the gravity term, density is treated as constant, equal to reference density, and in the buoyancy term, the difference between local density, which may vary with temperature concentration, and the reference density is multiplied with gravity and cell volume. This completes the discretization of all terms in the momentum equations. We now need to sort all these terms out and cast them into an algebraic equation involving as unknowns velocities at cell center and at the centers of the neighbor control volumes. On the left-hand side, we have one part of the rate of change term and convection fluxes. On the right-hand side, viscous forces, pressure forces, buoyancy force, and the explicit part of the rate of change term. The net convection and diffusion terms involve the sum of fluxes over all control volume faces, assuming that the unit surface vectors at all faces are pointing outward. In the computer code, fluxes are computed only at faces E and n. The flux at W phase of one cell is the negative of the flux at east phase of the preceding cell, and so on. Viscous fluxes are split into an implicit part which looks the same as diffusion flux in the generic equation, and the extra part whose net effect is zero when fluid properties are constant. For this reason, it is treated explicitly, that is, computed with variable values from previous outer iteration and moved to the right-hand side of the algebraic equation. Once everything has been sorted out, the usual form of an algebraic equation is obtained, where subscript k runs over immediate neighbor cells surrounding cell P. The matrix coefficient for u velocity contains contribution from convection fluxes, here from first order up in approximation, and from the implicitly treated part of the viscous forces. For all conservative methods holds, the coefficient on the main diagonal is equal to the negative sum of the neighbor coefficients plus the contribution from the rate of change term. The net source term is computed by adding pressure and buoyancy forces, the third correction part for convection fluxes, the explicit part of viscous forces, and the contribution from the rate of change term. When we solve the momentum equations at outer iteration m using the above defined coefficient matrix and source vector, we obtain the velocity field v star. In general, this velocity field does not satisfy the continuity equation. When we compute mass fluxes through control volume phases using the formula from slide 16 and velocity v star, and sum over all phases of the scalar control volume, we obtain an imbalance. The mass fluxes need to be corrected to eliminate this imbalance. For this purpose, one can use either simple type algorithms or fractional step methods. Here, the implicit fractional step method with acronym IFSM will be used. Following the IFSM methodology described in slides 12 and 13, we now seek to correct the velocity in the rate of change term and the pressure such that the corrected velocities satisfy the continuity equation. This leads to the following relation between velocity and pressure corrections. Taking into account that the volume of U cell is equal to the product of this cell phase and this distance, and analogously for V cell as this cell phase times this distance, one can rewrite the expressions for velocity corrections as follows. These are the expressions given in slide 13. We now request that corrected mass fluxes satisfy the continuity equation. Thus, the sum of mass flux corrections plus the sum of mass fluxes computed with V star, which results in the imbalance defined in slide 20, must be 0. When we substitute velocity corrections by the above expressions featuring the gradients of pressure correction, we obtain an algebraic equation for pressure correction. It is the discretized form of a Poisson equation with a source term corresponding to the mass imbalance resulting from predicted velocities. The matrix coefficients in the pressure correction equation are given by these expressions. The solution process follows the procedure shown in slide 14. When computing an unsteady flow, the time step is chosen such that it satisfies the accuracy requirements, that is, the velocity variation in time step is adequately resolved, for example, circa 100 time steps per period of oscillation. There are no stability criteria that impose limits on time step size. In lecture 20, the performance of this method will be compared with that of a non-iterative version of a fractional step method, as well as with simple type algorithms. When computing the steady state flow, the time step can be large, but not too large. CFL numbers defined by these expressions between 1 and 100 usually work well. Examples of application and comparisons with simple type methods will be presented in lecture 19. Implementation of boundary conditions will also be described in lecture 19. Here is a brief summary of this lecture. Fractional step methods are widely used in research codes for the simulation of unsteady flows. Non-iterative versions use explicit time advancement methods for convection fluxes, and are thus subject to time-step size restriction for stability reasons. Non-iterative methods include an additional discretization error of second order in time. It is usually small enough with time steps which are below the stability limit. Implicit methods require outer iterations within a time step when time-accurate simulation is required. Linearized equations do not have to be solved to a tight tolerance in each outer iteration, as is the case with non-iterative schemes. Implicit iterative methods allow the use of much larger time steps than non-iterative schemes. For the same time step size, the accuracy is higher than with non-iterative methods because non-linearities and deferred corrections are updated in outer iterations.